Let's turn our attention to the second main type of compounds or bonding, and that's known as covalent bonding. So we'll look maybe at some quick descriptions or characteristics of covalent bonds, and then we'll use a tool called Lewis structures or Lewis diagrams or Lewis dot diagrams to help us sort of understand what's happening with the electrons in covalent compounds. So first off, a definition: a molecular compound is formed when atoms, rather than transfer, when they share electrons. So if they share electrons, it's known as a molecular compound, and the bond is known as a covalent bond. So for example, here I have hydrogen, and here I have chlorine. Hydrogen, as it only has one electron, wants to have two electrons. It's going for two electrons in its outside shell or valence shell. Chlorine is going for 8 electrons. Currently it's got 7. Currently this one only has 1. So if this one can add 1 and this one can add 1, they'd be happy. But notice that they each need to add. Not the case of like sodium and chlorine, where sodium wants to get rid of 1 and chlorine wants to take 1. In this case, they're both needing an electron. So rather than one being transferred to another place, they share electrons like this. So here, in this case, I've got chlorine with 7 of its own, and sharing 1 from hydrogen makes up 8 electrons altogether. So it'll look like the nearest noble gas. 8 on the valence shell, it likes that. Whereas hydrogen, you look at hydrogen, and hydrogen, it has 2. And I said earlier hydrogen was wanting to have 2 electrons. So hydrogen is happy. It might not be a total happiness, like it doesn't really have 2 of its own. It has 1 and it's sharing 1. Same thing with chlorine. It's got 7 and it's sharing 1 to make it 8. But at least there's a nice compromise, a nice balance that happens here. And that balance, or that sharing of electrons, is called a covalent bond. Now, different than ionic compounds, we can actually talk about a molecule of hydrogen chloride, because when they exist in a compound, there aren't those lattice structures that are developed with ionic compounds, but each one of these is like a separate molecule. There may be slight attractions that we'll talk about in intermolecular forces between them, but typically they are their own molecules. So when we're writing a molecular formula for hydrogen chloride, it's not an empirical one, it's actually a molecular formula. For hydrogen chloride, then, it would be HCl, 1 hydrogen for every 1 chlorine. Now, I've in a couple of scribblecasts, we've looked at these things called Lewis structures, or I've used them, and I wanted to look a little bit more and play with it a little bit, just to give you a bit of practice on how you can use Lewis structures to help you get an idea of what's happening with the electrons. So, Lewis structures help us theoretically determine how 2 or more atoms are either transferring or sharing electrons. Most of the work we'll do here will be the ones where we share electrons. So for example, hydrogen, if you look at hydrogen in a periodic table, let me look at that. Here's a periodic table. Hydrogen is right up top here. And so hydrogen is in something called group 1. Notice the number 1 up there that I covered up. Group 2, group 3, etc. But it's in group 1, and what that means is it has 1 electron on its outside level. And we know that electrons are where all the action happens in bonding of elements. So what we're really looking for are the electrons on the outside level. Those are sort of the ones available for either transferring or sharing of electrons. So all of these compounds or elements in group 1 all have 1 electron, and you'll notice the charge on all of them is 1+. All of them have 1 electron available for either sharing or for transferring. Now, over here, you'll look at these other groups like this one here. We used to call it group 7 for now in this periodic table they have it as 17. But in this column here, fluorine, chlorine, bromine, etc., notice that they all have a charge of 1 minus, indicating that they are happy to take on 1 electron. Another thing that indicates, if they're only willing to take on 1, and I know 8 is the optimal number, all of these must have 7 electrons in their valence shell. Thus, if you look at the number up here, it says 17. You might maybe do some math, and I don't know, for some reason, subtract 10, and that would tell you how many valence electrons there are in that group. Actually, that subtracting 10 works quite well, because this next group, often called group 6, are ones where if you subtract 10, you get 6 electrons, and that's how many electrons are in the outside shell. And if you look at all of these ones right down here that are nonmetals, you'll see the charge is all 2 minus. So in other words, they want to take 2 electrons to become that stable 8. So if we know how many electrons are in the valence shell, then I can use Lewis dot diagrams to sort of help me play with what those electrons will do. Okay, we've already talked, I guess, about chlorine. It was in group 7. It has 7 electrons. I sort of like how I illustrated it here. Since noble gases have 8 valence electrons, and since chlorine is 1 to the left, chlorine's got to have 7. Oxygen is 2 left, so it has to have 6 electrons. So it's faulting or needing 2. And notice how I've drawn oxygen here. So oxygen has 6 electrons, and I've arranged them such that it looks like there's 2 empty spots. And that'll help us when we are putting compounds together. Notice chlorine here, it's got 1 empty spot. Or hydrogen, one of these hydrogens here, it also has 1 empty spot. So in just looking at playing around with these compounds, I could, to make something that's happy, hydrogen wants to have 2 electrons, like I said earlier. So if I come in here and just throw this one right in there, that's a nice situation. Hydrogen's got its 2, chlorine's got its 8. How about let's do that with this oxygen over here. If I bring a hydrogen in, hey there, hydrogen's happy because it's got sharing 2 electrons. But oxygen here only now has 2, 3, 4, 5, 6. I guess it's sharing 7. It'd be nice to have why don't we just grab this other hydrogen, slip it right in there. Oh, now there's a nice situation. Oxygen's got 8 electrons now, that it's either its own or it's sharing, and each hydrogen has 2. That's a beautiful situation. Everybody's sort of quasi-happy. That molecule there, of course, is H2O, or water. Let's play around with making some Lewis dot diagrams. So, for example, if I look at calcium, take a look at calcium and which column it's in. So I look here, I see calcium. Oh, calcium is right there. So calcium is in the 2nd column, indicating that it has 2 valence electrons. And right here, having a charge of 2 plus sort of confirms that. So if I'm going to draw calcium, I'd probably draw a calcium with 2 electrons, sort of like that. How about sulfur? Let's look up sulfur. Sulfur, right over there. It's in group 6. It needs 2 more electrons. So if it's in group 6, it has 6 electrons. I like to draw the electrons this way, that I give an electron to each side. So I envision 4 sides of the molecule. And then, so that's 4, and then now I start doubling up in order to make up how many of it has. So sulfur has 6, so I've got 4 so far, so I'll add 1 more there. Instead of adding another one here, I'll add another one here. It's sort of like you can think of each side gets 2, then it's full. You can sort of think of it that way. So here sulfur has 2 electrons that it's lacking. Like to get 8, it'd be nice to have another electron there, another electron there. Calcium has those 2 electrons, so there's probably a nice arrangement that these two could have. But I wasn't looking at the bonding there. I was just looking at the Lewis structures. Now, iron's an interesting one. When you look at iron on the chart, right there, it has two different charges. So iron will actually play as giving 3 electrons, or iron will give 2 electrons. That's sort of more difficult with iron to draw that, and I guess a question would have to tell you how many it would have. But you could do similar to calcium, draw an electron there, an electron there, and that would be Fe2+. Whereas if you drew it like this, iron 1, 2, 3, you would say that would be iron 3+. Often you don't see iron actually in Lewis dot diagrams, but that's one representation of how you could do it. Okay, take a minute and take a look at these compounds here that I've got and see if you could mix them up. Try and get a compound where, like these big ones, chlorine, oxygen, sulfur, where they have 8 electrons, and the smaller guys, these ones over here, have gotten rid of their valence electron, or are sharing that valence electron. I'll give you a second, play around. You can pause, and then I'll just sort of play a little bit here too. Okay, hopefully you're back from pausing. Let me start with chlorine. I put chlorine down there. It'd be nice to have one more. Here's a hydrogen. We've already seen that molecule a bunch of times. That's a nice situation. But how about a calcium? What if I came down here with a calcium and put a calcium there? Now, that right there is real happy for that chlorine. It's got 8. But calcium here, it's sharing the 1 electron, but now it's got another one that's a little lonely. Maybe I could bring another chlorine down. If I brought another chlorine down, I might need to twist it. I don't know if I can twist it. Oh, there I can. There. Yeah, it might look a little funny, but bring that in there. Now I've got a happy situation. So I have 2 chlorines for 1 calcium. And that's a nice compound. Okay, let's get rid of those guys. And how about bringing oxygen down? If I bring an oxygen down, maybe it might be happy like that. Oh, but oxygen's needing another one. How about we throw a hydrogen in there for that? Oh, that's not too bad. Oh, but that calcium there is still needing to share another electron with somebody. Maybe I guess I could throw another hydrogen in there. Oops. Grab another hydrogen, put that there. That would make for a happy molecule. I'm not sure what you would call that, but hopefully you're getting the idea of what we're doing. So with Lewis diagrams, or Lewis dot diagrams, I can take elements or atoms and specifically look at how many electrons they have, and then see if there's a way that I could maneuver the electrons so that a compound like sulfur has 8 hydrogens or 8 electrons around it, and a molecule or an element like hydrogen has 2. Here's another real nice situation. Sulfur's got 8, whereas each hydrogen has 2. That's what we can do with Lewis dot diagrams to help us sort of conceptually look at what's happening with the molecule. Just for information, this is H2S. That's that gas that you don't want to mess with. Okay, here's another example that we've done before, and just sort of, a bit of information on this one. If I take this and I put it together, I get a nice sharing of electrons. That's a covalent bond. When they share, just looking at to quantify that, when they share, notice that the electronegativities here, the difference in them, 2.2 to 3.2, the difference is only there is 1. And on that chart that we saw in the last Scribblecast, a difference of 1 says that the molecule is polar. And we'll talk more about polar here in a bit, but it means that the molecule is polar, and that has some implications to the properties of that particular molecule. actually, because it's polar, it'll probably have an increased boiling point, might have an increased melting point, and it might have some implications to its solubility. It probably will dissolve in water, and it'll have implications on how it reacts to other compounds as well. Okay, just as a last example on Lewis diagrams, here's an interesting one. We'll make a molecule of methane. If you look at carbon, it's in group 4, meaning it's got 4 valence electrons. It's a share guy. It likes to share. And this particular carbon, or this particular molecule, will actually share with itself. So if I have 2 carbons like I do here, they will share with each other so that these 2 carbon, or these 2 electrons, one belongs to here, one belongs to here. So it shares there, and then it can share with that one, and it can share with this one. Here's another hydrogen that can share, another one, another hydrogen over here, and the final hydrogen there. So now if you look, each hydrogen is sharing 2 electrons. It's happy. Each carbon in the sharing is sharing 8 electrons. That's a real nice situation there. And this compound, like I said, is known as ethane. And this compound would be known as a non-polar molecule. And we'll talk more, like I said, about that polarity. So covalent compounds are ones that share electrons. And Lewis diagrams are ones that are quite handy to help us determine how those electrons are shared.